Okay, I guess it's a good time to start. So good morning, everyone. Today is our last day for summer school, and today we are honored to invite Professor Yang to join us. He's a professor at UC Santa Barbara. As you know, he's an expert in graphene systems. He has created many impact in graphene quantum Hall physics and twisted bilayer graphene very recently, and he's still moving very fast. We hope we can see his most recent work in the next hour. But before we start, I want to note that if you have any questions during the talk, please type them in the Q&A box located at the bottom of your Zoom window. Also, in that Q&A box, you can upvote questions that you think are particularly important. And at the end of the lecture, I will read out a few of the most popular questions to our speaker. So without further introduction, the floor is yours.
Thanks. Yeah, thanks for the invitation and the opportunity to give a kind of overview of some of the work that mostly focusing on the work that we've been doing in my group over the last year or two on orbital magnets in graphene heterostructures. So let me start with just a very basic idea of the origin of magnetism. So magnetism comes from the repulsive Coulomb interaction and its combination with Fermi statistics. So the most elementary example, which you can find in Landau-Lifshitz quantum mechanics, is just considering two finite square wells and thinking about the effects of Coulomb interactions on the ground state of two electrons in a pair of square wells like this. And so you can write down symmetric and anti-symmetric combinations of the lowest energy states in the two square wells and calculate the splitting due to the Coulomb repulsion, and you'll get something finite, which will in general give you a splitting between those symmetric and anti-symmetric states. And what happens in a ferromagnet is that that splitting favors the anti-symmetric orbital state. So in other words, E minus, the energy of that anti-symmetric state, is lower than E plus, and that means that anti-symmetric orbital wave functions are favored. Of course, since the electrons are still electrons, they're fermions, the overall wave function has to be anti-symmetric, and that means that you have to have a symmetric spin wave function. And the ground state of that spin wave function, of course, is one where you have all the spins aligned. That's a symmetric state that that can be the ground state, and so that's basically the origin of ferromagnetism. Now, in solids, electrons also have kinetic energy, and they occupy bands. And so when you have a finite bandwidth, there's an additional criterion that has to occur besides just having a ferromagnetic coupling. You also have to have it be energetically favorable to polarize at all, because it costs you some energy in terms of bandwidth if the electrons can move. And so this is summarized by the Stoner criterion, which basically says that if you have electrons in a band of a given width, then you need the strength of that exchange coupling that splits your symmetric and anti-symmetric orbital states to be stronger than the bandwidth. That's because if you try to singly occupy these states as you would for a ferromagnet, then you have to fill your whole band. For example, when if you're at half fill, you would fill all the states in the band with just one spin. But if you can doubly occupy them, you'll save on bandwidth even as you compromise on exchange. And so this gives you a kind of crude requirement for ferromagnetism, and indeed basically a statement about when interactions are important at all. So the great example of this, the ubiquitous example is d orbitals in transition metals. Those are where we typically find ferromagnetism in materials, and those are basically relatively narrow bands, and so it's easy for them to ferromagnetically polarize. Now, in two-dimensional systems, which is what I'm going to be talking about today, you typically also need some anisotropy to get ferromagnetism. That's usually provided by spin-orbit coupling to make these types of 2D magnets more Ising-like rather than, say, Heisenberg-like. I'll discuss that in more detail a little later. So, okay, so I'm going to talk about graphene. So graphene is a pretty unlikely magnet at first blush. You have very delocalized 2D orbitals, so that's already bad. You'd rather have localized orbitals. It has a very low density of states, so it's very hard to meet that Stoner criterion because density of states basically vanishes at the Dirac points. And there's no spin-orbit coupling to speak of. So, so at first blush, it looks like this is not really going to be much of a magnet. Now, one of the things that that saves you and that will save this this effort is that this issue of having no spin-orbit coupling and therefore no anisotropy, at least, is going to be sorted out by just taking a different view of what you mean by magnet. And in particular, this talk will focus on really fundamentally orbital magnetism, mostly stemming from the fact that the Dirac valleys, when you gap them, have a finite orbital moment, and that orbital moment is relatively important ingredient. And in particular, it's a large orbital moment, something that can spontaneously order and has a lot of anisotropy because it's coming from actual 2D orbits in the graphene plane. Okay, so the way you can think about orbital moments in kind of the modern, context is just as functions of the Bloch states. If you ignore, well, really just the sum over which states are occupied in your Brillouin zone, and there are contributions when you calculate essentially the angular momentum operator and the basis of these Bloch states from the wave, what gets called the wave packet self-rotation, as well as the center of mass motion of your Bloch wave packet. This orbital magnetization is actually present in every material in principle, but it's usually small in magnets compared to the spin magnetization. There are some exceptions. So for example, there's this samarium aluminum compound that was discussed, about 20 years ago, which, here it says a ferromagnet having no net magnetic moment. This was interpreted as a ferromagnet where you have some relatively small spin polarization, but then about equal size orbital polarization, so that there's not much of a net magnetic moment left over. But typically, most ferromagnets, since antiquity, are based on the mostly on the electron spin rather than purely on this orbital magnetic moment. But there's no particular reason why that must be so, except that most of the time the spins are sort of an easy degree of freedom to order. That's different in graphene because of this absence of spin-orbit coupling, and also because it's a very natural way to generate large orbital moments. So, as was pointed out by Xiao and Shannu, the valley, in graphene, if you gap a Dirac point, that naturally generates a large orbital moment right around the gap, and that basically arises from this strong barrier curvature that happens at that Dirac point. So in graphene, you kind of have the perfect storm of being able to generate large orbital moments, but also having no spin orbit coupling in a 2D system, and so therefore probably suppressing the spin polarization, even if you were to meet the Stoner criterion. That's basically where I'm going to start with today. So the first kind of quarter of my talk, let me talk a little bit about flat band physics and twisted bilayer graphene. So the basic thing that we're trying to do is increase the density of states. Right? If you increase the density of states, you can meet the Stoner criterion. You can see some ferromagnetic polarization. So this is accomplished in twisted bilayer graphene by realizing this so-called magic angle structure, where you basically have an interplay of this interlayer tunneling and misalignment to generate band flattening at b equals 0. There's kind of a resonant condition where the bands get very flat, and as a result, you get this relatively flat, relatively isolated band near 0 energy. And lots of interaction physics shows up, right? So, this band can be isolated. You get insulators at commensurate filling of that band that indicates some broken symmetry, superconductivity, and ferromagnetism. I'm going to focus on the ferromagnetism for this talk and sort of how it may have some interplay with some of this other physics also. So the way we're doing our heterostructures, it's kind of important to notice because it's sort of relatively standard in the field at this point that you can build up these heterostructures by picking up two-dimensional materials and stacking them on top of each other. One of the key things that we are sort of religious about is making these heterostructures as clean as possible, certainly as regards charge disorder. So we do this by using graphite gates and hexagonal boron nitride gate dielectrics. The latter is standard. The former is not entirely standard in the field yet, but this allows you to realize extremely clean heterostructures with very low charge disorder, kind of comparable mobilities in, say, monolayer graphene to what you get in the cleanest 3.5 semiconductor systems. right? And to give some numbers, with this double graphite gating, you can get Landau levels that show broadening on the order of 7 or 8 Kelvin, and that compares to 2 or 3 Kelvin for, let's say, 40 million mobility gallium arsenide quantum well. So it's in the ballpark. And when we're lucky with twisted bilayer, you can get signatures of clean and homogeneous superconductivity in these systems also. So let me show you sort of one result, which is what happens in twisted bilayer graphene when you take that and you align it to one of these hexagonal boron nitride substrates in one of these relatively clean systems. In this case, that flat band structure of twisted bilayer is modified so you actually get 2 flat bands that are separated by an energy gap, and that energy gap comes from the alignment of the hexagonal boron nitride lattice to the graphene lattice. So that gaps out the Dirac points that are native to the monolayer graphene structure, but also to the twisted bilayer structure without this alignment. And it generates flat bands above and below 0 energy, in particular flat bands that have a finite Chern number in the non-interacting picture. Now, that Chern number, of course, has to cancel between the 2 valleys. So the K and K prime valleys have opposite Chern numbers, and the conduction valence band have opposite Chern numbers from the partitioning of that Barry curvature, if you want, the generation of that Barry curvature, which from gapping the Dirac point, which on net has to net out to 0. But that's your non-interacting band structure. And of course, these bands are quite flat compared to the scale of Coulomb interactions. And so the observation which we made is that at 3 electrons per unit cell, so what's plotted here is the resistance as a function of the charge carrier density. And I want you to focus on where this yellow arrow is, where you can see that at 3 electrons per unit cell, you have a deep minimum in the longitudinal resistance, RXX, and it's accompanied by a plateau in RXY of just around h over e squared, the conductance quantum. Okay, and it turns out that this is actually signature of a quantized anomalous Hall state. So if you sit at that density and you sweep your magnetic field, you can see that there's hysteretic transport and that the RXX vanishes and that RXY is more or less perfectly quantized to its expected value for a quantized anomalous Hall state. So, so this is consistent with at 3 electrons per unit cell, you are polarizing into a net 1 of these topologically non-trivial bands corresponding, for example, to polarizing into the one of the valleys. I'll note, and I'll talk about this a little bit more, that there are these large jumps. They're like Barkhausen type jumps in RXX and RXY, as you might see in a metallic ferromagnet that has crystalline disorder, say domain walls. Actually, it's exactly the same type of thing that Barkhausen observed in iron, where you may have domains that are jumping one at a time. So, okay, so the basic picture here, right, is the mechanism is kind of simple, which is that you have gap Dirac points and therefore orbital moments in the given valleys. Those valleys are anisotropic, right? These valley moments give you a fair amount of anisotropy, lets you have an Ising-like sort of Hamiltonian that will give you some ordering at finite temperature, and apparently interactions favor polarizing into one of these Chern bands, or into 7 out of 8 of those Chern bands, if you want to think about electrons, which give you a net Chern number and therefore a quantized anomalous Hall effect. Okay, and the numbers are interesting to look at because the numbers for the gap, for example, and the Curie temperature, because they're rather different. Quantized anomalous Hall effects have of course been studied in other systems, typically by magnetic doping of some topological insulated thin film, where the idea is kind of similar. You'd like to have a system that has Dirac points. That's why you have a topological insulator. And then you'd like to gap them out, in that case, by breaking time reversal symmetry. It's a little bit of a different mechanism, but the same basic ingredients. From the materials point of view, that effort in magnetically doped topological insulators has almost always yielded a Curie temperature that's high, but an induced energy gap for the electrons of that quantum anomalous Hall state that's relatively low, which restricts that effect to low temperatures, usually very low temperatures, at most a Kelvin. Here, the hierarchy seems to be different. So for example, when we measure the activation gap, we find activation gaps for these states at about 30 Kelvin, but the Curie temperature in these systems is only 7 or 8 Kelvin. So actually rather the reversed hierarchy relative to bismuth antimony telluride, where the Curie temperature may be 15 or 20 Kelvin, so several times bigger than ours, but energy gaps are maybe 10 times smaller. And I think, we understand this more or less as coming from being in the relatively clean limit, at least microscopically, and I'll get back to that, in these moire systems, as opposed to being in a regime of very strong microscopic disorder in these magnetically doped systems, where these chromium dopants are put in large quantities and
That looks cool, Bubble.
excuse me a second.
Bubble, that looks cool, Bubble.
Yes, it does. 1 second. Sorry about that. One of the interesting things that you can do in the system that we observed is that these orbital magnets are relatively floppy to things that to various, they respond to various voltages, currents, and so on much more than typical magnets. So for example, in this quantum anomalous Hall state, you can apply very small currents and flip this magnetization reversibly and completely. So with current densities that are very small compared to devices that have been made out of other magnetically doped topological systems. So you can use this, for example, to make a little current controlled magnetic bit, where you put a little current pulse and flip the magnetization up and down, and you can sort of do this over and over again. The mechanism for this is still not entirely understood. There are a few different ideas, but one in the literature that have developed since then, but one idea that we had is that really you can just think about some contribution to the free energy that goes like the current cube, that comes from the fact that when you drive currents through these samples, you're actually occupying some extra states on one edge or another, and when edges are asymmetric, either in their velocities or simply their lengths, you can bias towards one churn insulator state versus another. To give another example, let me switch to a related system, which is very similar. So actually, there's a huge issue with reproducibility in these. I'll get back to that later. So in particular, we were never able, despite some moderate efforts, to make a second quantum anomalous Hall device in twisted bilayer graphene. It's hard to align the boron nitrides and also have everything else work and everything be clean. And I'll explain why in a few minutes. But motivated by the basic idea of the symmetries of that system, which are that you'd like to start with something that has flat bands, but you'd like to strongly break the C2T symmetry that protects the Dirac points, because that's going to favor you polarizing into one of these churn bands. We studied a different system. So this is twisted monolayer on bilayer. So it's a monolayer that's twisted at an angle relative to a Bernal bilayer, and it generates very similar physics in that you have flat bands. Now, because the Bernal bilayer is tunable by displacement field, you can tune the electronic structure by displacement field, and you find that there's a regime of displacement fields and densities where indeed you see correlated insulator type behavior at nu equals 1, 2, and 3. And in fact, nu equals 1 and 2 are quantum anomalous Hall states. And this is a much easier system to make. I think we've made 3 samples, and 2 of them show exactly the same physics down to the details, the ones that are at the same angle. So this has sort of helped with that material problem. It's still, the quantization is not perfect, but at least now there's, you can see that this physics does reproduce. What I want you to notice are really 2 things. One is that, so in this system, it turns out instead of having those churn bands have a churn number of 1 per spin and valley flavor, they have a churn number of 2 per spin and valley flavor, and you see quantized anomalous Hall effects consistent with a churn number of 2. So the Hall resistance plateaus are at h over e squared divided by 2 rather than h over e squared. But I want you to notice another kind of strange feature, which is that in particular at nu equals 3, the data as a function of density and magnetic field is very switchy and strange. And in fact, the Hall resistivity is changing sign as a function of density in addition to as a function of magnetic field. That's in contrast with nu equals 3, or in contrast with most Chern insulators, where when you reverse the magnetic field, you polarize into one of the valleys, and that fixes the sign of your Hall voltage and of the Chern number. And so at first this seemed like it was noise and not a real physical effect we should pay attention to, but it turns out that that's not the case. In fact, what's happening is that the Hall effect is switchable between nearly quantized values, not only as a function of the magnetic field, which is plotted on this axis here, but also as a function of the, here's labeled carrier density. Really, we're just tuning the gate voltage. Okay, so let's look for an explanation for that. So I think there's an interesting feature of these, orbital magnets in general, and maybe orbital Chern magnets in particular, which is that, fundamentally in an orbital magnet, if you can ignore the spin, then all of your magnetization arises from your band wave functions. And which band wave functions you occupy, of course, depends on interactions, but it also just depends on how you make your system and details of your lattice, which of course is different in these different types of moire systems. Generally, it's a function of the chemical potential. As you fill these states, you're going to fill different block states, and then the total sum of this orbital magnetization is going to change. And that can be an arbitrary function. Nothing says it should be positive or negative or anything like that. It's just depends on the block states. And there's one particularly sharp situation, which is when you're in a gap. So when the chemical potential lies in a gap, then the only contribution comes from this Berry curvature term. And in fact, the contribution is just going to be proportional to the Chern number, because at that point, you're just counting the magnetization of your topological edge state. So if you have no topological edge states, obviously you're not occupying any new states as you change the chemical potential in a gap. But if you have chiral edge states, then as you change your chemical potential through a gap, you will have you will occupy them more and more, and they have a magnetization. They have some equilibrium current. Okay, so so as you cross a topological gap, you will contribute a delta M to the magnetization just from those edge states, which is C times that energy gap divided by the flux quantum, to give you the right units. Okay, and what we think is happening in these systems where the Hall effect can be switched with a gate voltage is simply that this bulk, that the magnetization from the chiral edge states may simply exceed that of the bulk, and in particular be of opposite sign, right? So so the basic picture was given by Alan McDonald and collaborators, for twisted bilayer graphene. It turns out doesn't work exactly this way in twisted bilayer graphene, but it does work this way in this system, where you can basically, because you can neglect the spin magnetization, which usually would dwarf these types of effects. Let's say in a magnetically doped topological insulator, you have a huge spin magnetization. These orbital effects make no difference. Here, everything is orbital, and you can get into a situation where, as you cross the topological gap as a function of your gate voltage, you simply reverse the sign of the magnetization. Now, the sign of the magnetization is defined for a given valley. And so let's say you start in the ground state, let's say in the K valley, and your magnetization is pointing in the right direction for the applied magnetic field. Then you sweep the gate voltage. Now you're no longer in the ground state. You're now in a metastable state because you've actually reversed the sign of the magnetization in that valley. So now your electrons are occupying the wrong valley for the sign of the magnetic field. If you have metastable dynamics to begin with, then it can get frozen there, and you can get a first order transition where it will simply flip. And that's basically what's going on here. So you can flip it as a sign of magnetic field, which of course couples to these opposite valley moments, but you can also actually physically change the magnetic moment of a given valley as a function of that applied gate voltage. And you can do exactly the same as with the magnetic field. So here is, again, as a function of time over a variety of actuation sequences, where what's shown on the top plot is the resistivity, the Hall resistance, right? And you can see that it can be reversibly flipped between positive and negative, both by sweeping the field. So you can do a little ramp of the field to switch your magnetization, but you can also do little ramps of the gate voltage to reverse it just as effectively. So you can really make a little purely capacitively switchable magnetic bit using this effect, because it allows you just to choose what the ground state valley polarization is as a function of applied gate voltage. Okay, so let me move on. So I think that the the message is there's lots of control in these systems, that, these orbital magnets give you some knobs that are, let you do some kind of spectacular actuation. Of course, they generate, these seemingly relatively clean, clean physics in terms of, let's say, the intrinsic energy scales. But at the same time, I think as anybody who's worked on these systems knows, they're not clean in the sense of reproducible or regular. There are certain features in all of these moire systems that are reproducible. So superconductivity is not that hard to see, right? At least in some form, but it's a little different every time. It's not like you're going to measure two samples and you're going to get the same TC to within 5%. Certainly for these magnetism samples, you see the evidence of disorder relatively sharply. Besides the fact that it's hard to remake the same sample, you see these Barkhausen jumps, right? That's telling you something about disorder, and they're actually quite reproducible in transport. So it looks like it's structure. So what we wanted to do is try to understand this microscopically a little bit better, so that we can try to understand, what's really limiting these samples, right? And so, so to do that, we're applying a technique called Nanosquid on tip microscopy. It's a very sensitive technique for measuring magnetic fields, which is what you need, because if you think about moment densities on the order of a Bohr magneton per superlattice unit cell, that translates into a magnetization in 2D. It has the same units of current of about 50 nanoamps, which means if you're trying to measure things, let's say at 100 nanometer resolution, that's a magnetic field of 100 nanotesla, which is sort of right at the limit of the best magnetic sensors, either these nanosquids or MV centers, and nanosquids have various advantages, not least of which is that we happen to have built one in my lab. So anyway, we're going to be using some nanosquids that have tip diameters typically on the order of 200 nanometers. We can make them out of indium, we can make them out of lead, and I'll show you some of our work trying to understand this twisted bilayer graphene quantum anomalous Hall sample and what some of its features are. So the way we do these measurements is to couple. We have this problem that we want to measure a static magnetization. On the other hand, the DC sensitivity of these squids is not very good. There's a lot of 1/f noise. So you'd like to be able to lock into some signal which is modulated in time. And so we do that by coupling the nanosquid to a tuning fork. That allows us to actually measure out the DC magnetization, but what we measure is a gradient of the DC magnetization. So it's coupled to a tuning fork. The tuning fork oscillates. We measure at the frequency of that tuning fork oscillation, and what that gives us is a derivative along the direction of that oscillation. So here I'm comparing some calibration data of a DC signal and then its derivative and what we measure in the tuning fork. You can see these two are very similar. This can all be calibrated, and you can understand exactly how much your tuning fork is moving and so on. And so eventually you can then reconstruct all the DC stuff. But just to let you know, this is how we're doing the first set of measurements. So to look at this orbital magnetism in twisted bilayer, we have to deal with the fact that the signals are small. We also have to deal with the fact that there are a variety of other artifacts that will crop up in these measurements, certainly when you're trying to push signal levels, including from electric fields and things like that. And so what I'll show you are antisymmetric combinations of measurements taken on different arms of the hysteresis loop, but at the same magnetic field. And so we can anti-symmetrize with respect to that sort of preparation of the sample, and that allows us to extract just the magnetic structure. And this is what it looks like for this twisted bilayer sample in the same regime that shows quantized anomalous Hall between these four contacts. And you can see that the structure is not at all uniform. But there's clearly magnetic structure, right? And in fact, using kind of standard Fourier domain techniques, you can actually just calculate this magnetization, and you find that indeed the magnetization is relatively large. It's larger than what you could get from spin. This only has effectively one hole per superlattice unit cell, but we find a magnetization of 4 Bohr magnetons per unit cell. So that moment has to come from somewhere. Most likely it's entirely an orbital moment, but at the very least it's 75% orbital moment. So that seems to check out. Then you can also look at its density dependence, right? And you can see that in fact the density dependence does very much what I kind of told you before. Here we're comparing the density dependence of the Hall effect in these sort of light blue symbols and a local measurement of the magnetic field in these white symbols. And you can see that where the Hall effect is in the gap, where it's actually quantized, that's where the magnetic signal actually just collapses very rapidly, which, again, makes sense with what I showed you before, where you have this large contribution from the edge states. And most of what you're seeing when you image this is actually contribution from, you could call them from the edge states, although the sample is quite disordered, so those edge states can be internal. It seems like that actually cancels the bulk contribution in a large range where you still see hysteretic transport, but you actually don't resolve any local magnetic moment within our sensitivity. So the thing that we're most interested in is understanding this domain structure, though, and what the origin of that disorder is. So you can see, for example, that in transport, you can stabilize the system either at full polarization of opposite signs, but also in a minor loop where you stabilize some mixed phase of positive and negative magnetization. And you can actually work out by comparing these scanning images taken at these different points, the nature of the grains that contribute to that Barkhausen type noise. So you can see that the difference between E and D is a flipping of this sort of mesoscopic sort of micron, several micron scale domain, and the difference between D and C is the flipping of a different domain. And so you can roughly make this type of picture where you say, okay, there's big grains and they have edge states around them. As it turns out, this picture is probably not really correct, and I'll show you. But nevertheless, it's quite different from what's seen in, let's say, chromium doped bismuth antimony telluride, where magnetization reversal does not occur by domains flipping. It occurs by these tiny little dipoles flipping, and they flip in a random way. Actually, in twisted bilayer, what we found is that these domains are very reproducibly flipped, and they're always sort of the same kind of relatively large micron scale type effects. So to try to understand this a little bit more clearly in terms of structure, what we've been doing lately is trying to map out the microscopics of the twist angle in these structures. So you can use an excited subband Landau level. This is a technique that pioneered by Ellie Zeldov to map twisted bilayer twist angles. Basically, you're just looking at the density where certain features appear that you know are correlated to twist angle. And we look at this device, and it's not a spectacular device from the point of view of twist angle uniformity. They're very, so what's plotted here is twist angle in this region where we could get signal, comparing it to, say, here's the device geometry and the magnetization measurements I showed you before. And there are patches of quasi-uniformity, but it's not really that uniform, and there's certainly some strong gradients. And this comes back to the fact that twisted bilayer graphene is not a structurally stable configuration of two graphene layers. They would prefer to be Bernal, and so you're always quenching strain into your into your final device, and it's sort of a dark art of whether you can do that better or worse, but it's hard to avoid completely. And so if you now plot the gradient, you can see that there are some places with very strong gradients, and then there are places with much weaker gradients with higher uniformity. And the basic takeaway that we've gotten from this is that if you draw, say, where some of the stronger gradients are, in other words, where a twist angle grain boundary is, that seems to correlate with where magnetic domains are pinned, not just with where the magnetic ground state has higher or lower moment, which sort of makes sense if you are different densities and have different twist angles, but actually where they stop. They seem to stop at these boundaries, and that's where you can stabilize them. And that's really identical to iron, where you have grain boundaries and the magnetic domains just stop at the physical grain boundaries. But these are grain boundaries in the twist angle. Now, a kind of intriguing thing is that if you then ask, why are we seeing quantized transport at all? The answer is not so clear, because what you can think about is that what we know from quantum Hall studies of these same types of materials is that there's really no charge disorder. There's no microscopic charge disorder. Any disorder is probably coming. This twist angle disorder is by far the leading candidate. So I think the way you can think about this is not in terms of some sort of self-averaged microscopic disorder and a mobility edge, but rather that you have a very locally clean system, that you have lots of twist angle disorder associated with that. So you have this intrinsic gap, which might be a few milli electron volts. And so in a clean system, and we see this in quantum Hall all the time, if you have a gap of 3 MeV, you should see a gap, you know, the width of your plateau should be 3 MeV in gate voltage. But actually this is several times, you know, tens of times bigger than that, maybe 20 or 30 times wider is the width of this quantized plateau. So to try to understand what's going on, what we can do is we can visualize the region in twist angle, the region in space where, given the twist angle which we've measured, you expect to be within, let's say, 5 MeV of the right filling factor, which is where you'd think the system would actually be incompressible. We can't actually image on the spatial resolution required, so we have to kind of construct things from this twist angle map and our this assumption that the size of the gap might be, I think here we put 10 MeV to be kind of conservative. So where's the system actually incompressible? In principle, it should be on the yellow lines. That's where you're actually at nu equals 3 plus or minus 5 millivolts, okay? And so you can play a video, and the video is gonna run through different applied gate voltages and show you where we think the system should be incompressible by this logic, okay? Oops. Okay, and so here, let me restart it. So, oh, it's playing. Here we go. There's the full video. Okay, so you can sort of go through, and in the quantized plateau, you see that yellow is just actually an extremely skinny ribbon that bridges the contacts. I'll play it again, but it is by no means you know, mostly quantum anomalous Hall. There's like a tiny ribbon that might have a width of 100 nanometers where the system is actually incompressible, and apparently we're measuring chiral edge states along that ribbon. Okay, which is kind of surprising, right? Because the quantization is reasonably well maintained, but I think it starts to give us a few ideas about the microscopics. One is that apparently for quantization to be maintained, it means that even on a tiny narrow ribbon, here you can barely see the ribbon, but it would be continuous. It's maybe only a few more unit cells wide here, and yet it's still quantized, which I think tells you that the edge states are localized probably to within about a single unit cell of the boundary of the incompressible region, which is sort of what you'd expect. Another is maybe this gives us some explanation for why a 2 nanoamp current is enough to have a big effect. It's because, you know, these are actually really tiny samples. We think they're tiny a micron, they're actually tiny more on the order of 10 nanometers in terms of where the actual quantized Hall state is. Okay, so I'm going to stop talking about twisted bilayer there. Maybe you can tell me how much time I've got left.
You got 22 minutes.
Perfect. Okay, good. So very good. So I'm going to talk about a different system now, and a sort of different way to try to affect this physics, right? So, you know, I've shown you some of the kind of positive and negative aspects of these moire systems. So in particular, you know, you certainly get strong interactions. You can get topological states, which is, you know, something that we like to see. You can play around with them. They seem to be nice, clean realizations in some ways, but they have this pernicious issue of this kind of mesoscale disorder. It's not self-averaging disorder. It's not something that you can think about as being uniform in any way. They're really things that are non-uniform on the scale of a reasonable fraction of the scale of the device. So, you know, 100 or 200 nanometer domains at best, and you know, a lot of this mesoscopic scale disorder, it's very annoying. It really impacts reproducibility in a way that even microscopic disorder would not. So what we'd like is really clean correlated 2D system, right? So what does that mean? We want to have high density of states, and we'd like it to be metastable or ideally stable. So actually, you know, we don't have to invent something new here, right? This is an idea that's already been around for a long time. We just noticed regular bilayer graphene. If you take regular bilayer graphene, its band structure is described by sort of some subtle Dirac points that are really closer to a parabolic band touching overall. And when you apply an electric field, you gap out those Dirac points and that, you know, quasi-parabolic band touching, and you get quartic type bands around, which give you a very high density of states. In particular, there's a divergent density of states that goes like 1 over square root of n, right? And this was already predicted, you know, almost 15 years ago now, that this should be a ferromagnet at low densities, and you know, a lot of the physics that we found in twisted bilayer should be similar. You need a very clean system, and you know, we looked at this actually already, you know, several years ago, and you can see this is now measurement of the capacitance. So this, you can read this off as inverse compressibility. So a big peak here when you have an applied displacement field is where you have a gap at charge neutrality in bilayer graphene. We didn't see any signatures of ferromagnetism. If you look at the low density, you see these sharp dips. Those are the Van Hoff singularities at the band edge. But the hypothesis that we can explore is whether this is a matter of degree rather than of kind. In other words, like maybe the idea is right, but I don't know, the samples weren't clean enough, or it's just the density of states is not quite high enough. The Stoner criterion in this, okay, it's naive model, but it's kind of a sharp thing. If you're below the Stoner criterion, not much happens. And if you're above it, you get a first order transition to something ferromagnetic. So, you know, as again, has been noted, certainly not the first time by us, rhombohedral graphites are very similar, but kind of more so. They're quantitatively more strongly interacting in the sense that density of states is higher, but qualitatively, you know, they have the same symmetries as bilayer graphene. So so that the way you can see this is in a very simplified model. You know, Bernal bilayer graphene basically has a p squared dispersion, which gaps out to p to the fourth. And ABC trilayer graphene, which is the system I'll tell you about, has a p cubed dispersion, which gaps out to p to the sixth. So the density of states peaks are that much higher, and everything should sort of be that much more. You can do this a little bit more sophisticated way. So here's like 6-band model of ABC, and this is the electronic structure with and without an applied displacement field. And you know, you can see there these big density of states peaks. There's some intricacies to the Fermi surfaces that actually occur, you know, within these bands here shown for this 20 MeV interlayer splitting. You get, you know, some kind of complicated fermiologies at low densities for electrons and holes, but basically it's a high density of states. Okay, so that's what we're going to look at. So to make these samples for the interested, right, it's kind of interesting. You know, they have this problem that ABC is metastable. It's not unstable, it's metastable. So it's an energy minimum in the structure, but it likes to relax to ABA. So there's some tricks you can use to try to stabilize these ABCs. The good news is that this tends to fail completely or not at all. In other words, you don't generally generate mesoscopic disorder of ABA and ABC domains. You typically either get a sample that's entirely ABC or is entirely ABA. And the reason is that if you have mixed domains of ABA and ABC, there's basically always a pressure on the domain wall from the ABA side to shrink the ABC domain. And when you make these structures, so when you do your transfer, when you do your lithography, your heating and cooling, those domain walls will typically move until there's no ABC left. So the only way we found to actually stabilize this is to remove all ABA, and then there seems to be a reasonably large energy barrier to nucleating a new ABA domain. So if you start off with something that's purely rhombohedral ABC, then it will stay that way. And the good news is that if your samples fail, they fail, but if they don't fail, they are, as far as we can tell, perfectly uniformly ABC without any stacking faults that show up in any way. So, so I'm going to show you some more inverse compressibility data to start with, right? So this is ABC trilayer graphene at 0 magnetic field. And the claim that I'll make is that almost everything you're looking at is actually a ferromagnetism. There's one exception, which is, you know, this step in density of states, which is basically given, you can see it here. That's the only thing that seems to be a single particle effect. And that comes from a detail of the band structure where for holes, you at high density have this sort of regular Fermi surfaces. So here I'm showing them for the 4 different flavors of spin and valley. And as you lower the density, actually there's a Lifshitz transition to an annular Fermi surface. It's actually one of several transitions. Let me show you, you know, just to show off a little bit how clean these systems are. There's another way we can try to do the fermiology at 0 displacement field, which is to look at quantum oscillations. So here are quantum oscillations in this structure plotted over the same range. So this is charge neutrality, and here's where that kink was. I want you to notice the scale here, which is that the maximum field applied here is 1 Tesla. So you can see quantum oscillations very clearly starting at, you know, well under 100 millitesla, and then you can actually then take the Fourier transform of these to really map out the fermiology. So in particular, what you can see, so what we're doing here is we're going to take this quantum oscillation data, we're going to plot it as a function of 1 over b, and then take the Fourier transform of that. That's sort of standard. That gives you a frequency in Tesla. And then we're going to normalize that by the total charge density. So what's plotted here is a function, is the Fourier transform as a function of what I'll call F nu, and F nu measures the fraction of the total electrons in a given Fermi surface. Okay, so let's start off on the left. This is at high densities where we think the Fermi surfaces are simple, and you see that F nu has a single peak at 1/4. Okay, and what that means is that you have extremal orbits of the Fermi surface which encompass 1/4 of the total density. Okay, which is exactly what you'd expect if you just have 4 Fermi surfaces. You know, 4 regular Fermi surfaces, that's what you expect to see. Okay, so there's your fermiology of the high density regime. And then you can see that as you lower the density, you get a transition where this extremal orbit starts to grow. And at the same time, you nucleate a new orbit. And that's exactly what you'd expect at a Lifshitz transition, where you now take in this case, a hole-like Fermi surface, and you nucleate an electron-like pocket inside. Then, as you keep moving down in density, what you see is that there's a rather sudden change, and you go from having this big and small one to now actually the prominent peak goes to 1/12 of the total Fermi surface volume is in a single Fermi surface. And that's, again, actually what you'd expect from single particle physics. You have now, this is where this Van Hove singularity occurs. That Van Hove singularity is coming from the saddle point, where these 3 pockets, where you go from an annulus to having 3 pockets. And at that Van Hove singularity, that's where you have this transition in the Fermi surfaces. Okay, and on the whole, on the electron side, it's a bit simpler. You don't really have much in the way of an annulus because the trigonal warping and other hoppings contribute in a certain way. I won't say much about that just yet. Okay, and so basically at 0 displacement field, there's not too much sign of interactions. There's a little bit, but I'll talk about it later. But at high displacement field, it's very different. This doesn't match single particle physics at all. And in fact, you can see this because there's lots of negative compressibility, which is not a single particle effect, but usually happens when there are non-uniform states in your 2D system. So, classically, you get it in a Wigner crystal, but you can also get it at first order phase transitions where you have phase separation. Okay, and so if we look, let's focus on the electron side. You can look carefully at these different phases separated by these sharp first order looking type transitions, and you can see that in fact the degeneracy of these Fermi surfaces is different in these different regions. So in particular, out at high density, you see a peak at 1/4. That's, again, just means you have 4 Fermi surfaces that have the same volume. Then in this intermediate region, you have a peak at 1/2. That's, again, now telling you that you've lost one of the spin and valley degeneracies. So now you have 2 Fermi surfaces. And at low density, you have 1. So basically, you just, each of these lines is a phase transition between regions of different Landau level degeneracy. So you can try to capture this with the Stoner model. It's the simplest thing that you can do, right? You can put in a realistic band structure and sort of see what comes out. And indeed, you get something that looks reasonably similar. You can see that the trajectories of these lines are basically just directly related to the evolution of density of states in the single particle model, right? It captures that sort of density versus displacement field behavior. It's interesting that it actually predicts phases that are not seen. So in particular, a phase that has 3 Fermi surfaces rather than just 2 or 4. You can fix this with a kind of Hund's rule type interaction. Generally, you can just choose any 2 flavors and say it's energetically favorable to fill 2, but not energetically favorable to fill an odd number. But actually resolving which flavors are favored theoretically is not so easy. It's easier to do that experimentally. So you can look, for example, at the in-plane field dependence of some of these transitions, and you can just see that the 2x and 1x phases are both equally favored by the in-plane field. So they're both, we presume, spin polarized, assuming the in-plane field couples mostly to the spin degree of freedom, whereas, of course, the 4-fold phase is not spin polarized. So you can more or less figure out what all of these phases are. It's interesting that in this system, it seems as if this Hund's coupling is favoring spin polarization rather than intervalley antiferromagnetism, which is more typical, let's say, in graphene quantum Hall systems. And also people thought this system at least at low displacement field. You can confirm this by looking at anomalous Hall effects. So the picture that we have here is that the 1-fold phase is spin and valley polarized. The 2-fold phase is valley unpolarized but spin polarized, and that's consistent with this. But we can check that valley polarization by looking for anomalous Hall. Anomalous Hall, of course, comes from the same Barry curvature, which again cancels between the valleys. And you see that in this 1-fold phase, you have a strong anomalous Hall, whereas in the 2-fold phase, you don't, and that's again sort of checks out. So an interesting question here is, wow, this is all kind of obvious physics, right? What about bilayer graphene? You know, why is this not there in bilayer graphene? After all, the Hamiltonians are almost the same. And actually, it turns out that you know, we just missed it. So this is a device that actually we made like 5 years ago, and just went back to look at now, armed with this new knowledge. And it turns out actually that this type of ferromagnetism is also there in bilayer graphene, and it's pretty robust. It's just at considerably lower densities, and in particular, considerably higher displacement fields than it is in the rhombohedral trilayer. So these, you know, these kind of ear butterfly looking features are all, this is a one-fold phase and a two-fold phase, and this is just Bernal bilayer graphene. There's nothing special about it. But I think the key thing is that, you know, the Van Hoff singularities in bilayer graphene really do stick to the band edge. So this is always low density physics, whereas in ABC trilayer, they tend to be actually at finite density, and especially for holes. And so that makes it just much easier to see, including at low displacement fields. You'll notice that the displacement fields here that we have to go to get these to be at reasonable densities are really very, very big. So it's not every device that can go this high. But anyway, all of this ferromagnetism physics seems to be there in Bernal bilayer graphene also. Okay, so in the last few minutes, sort of let me walk you through some more of the zoology of these ferromagnetic phases, in particular for hole filling. It's much more complicated. There's lots more transitions, right? There's some simple regions. So here I'm showing you know, the same compressibility data, but taken at finite magnetic field, where you have one-fold and two-fold and four-fold regions that look relatively simple. But the band structure here is more complicated. Even at large displacement fields, the Van Hoff singularities at finite density, you have lots of different Fermi surface topologies, even just in the non-interacting picture. And so there's, you know, at least a few you know, a few interesting things to say. One is that actually, you know, for the hole side, is much harder to see for electron side. You can get actually hysteretic anomalous Hall. So you could really see this is a ferromagnet, and that it's breaking time reversal symmetry. That's very obvious because you can actually hysteretically stabilize it. One interesting thing is that these transitions always occur by a single jump. We've never seen Barkhausen type jumps the way we ubiquitously do in Moiré systems, because I think these systems just effectively have no disorder and nothing to pin those domains, even at very low temperatures, at least so far that we found. Actually, they're so first order and sort of so stable that you can actuate hysteretic switches again by gate voltage. Here, this is not the same effect as what I showed you before. This is really just you have a first order transition as a function of gate voltage, and between a polarized and an unpolarized state, and that is also hysteretic. So here I'm sweeping the displacement field across this transition, and there's a lag, and you can stabilize in either this is a fully spin and valley polarized phase, or one that is spin and valley unpolarized completely. But then there are also these much more complex regions, right? So besides sort of these quantitative things, there's difference qualitatively. So there are these regions in between where I've labeled 1x and 2x, where the Landau levels are very complicated. Same thing between 2x and 4x. So it turns out there's two different, they're basically all Lifshitz transitions, but there are two types. There's one where you just change the Fermi surface topology as you do in the single particle picture, and also where you can change it because you can unbalance your isospin occupation. So for example, you can look across here and see that these are, you know, many of these features are replicas of the same Lifshitz transition from the non-interacting model, but replicated for 2 or 1 flavor. And but at the same time, you can also have states where you have you go from, for example, 4-fold polarization of a simple Fermi surfaces to 4-fold, no polarization of annular Fermi surfaces, but then regions where you actually have some kind of mixed degeneracy. So if you look at quantum oscillations, you can see that you have regions which are simple, regions which are annular, and then regions which are simple, but in between there's something where you have some small Fermi surfaces and approximately, let's say, some broken symmetry, maybe a majority and minority in one valley. So majority carriers in one valley, or one spin, and minority in the other valley or the other spin. Okay, so we can basically flesh out this phase diagram, and that's it's very complicated for a system that has absolutely no moire, right? This is a perfect crystalline basically graphene system where we've just increased the density of states a bit by using these band edge Van Hook singularities. So in the last minute, I'm just going to quickly mention, the nice thing about these rhombohedral layers is that they start off very perfect, but you can actually add a moire if you want to sort of isolate the physics of the moire specifically. And it's interesting because apparently a lot of the physics of interactions is already there. So what is it the moire actually gets you? And the key thing that it gets you is gaps. So it gets you gap states away from charge neutrality, because if you want to have an incompressible state, you should be at some commensurate filling of a lattice. And in graphene, the only reasonable denominator commensurate filling is 0. But if you put them on a moire, of course, now you can be at nu equals 1 or 2 or 3 at some moderate densities, which happen to overlap with where the interactions are already strong. So let me just sort of show you the comparison between a system with no moire, so ABC trilayer with no moire, and one with a moire. And the basic message is that the correlation physics is very similar, but now you can have insulating gap states at finite density. So you're seeing here as at nu equals -1 and -2, you have incompressible states. Those are basically your correlated insulators. You also have a incompressible state at nu equals -4. That's the edge of your moire band. But actually, all of these other magnetic phase transitions are largely similar. They don't seem to care too much about the presence of the moire potential, actually. And we can understand this in a simple way, which is to say that apparently the Coulomb repulsion is just stronger than the moire potential itself, right? And so what's happening is that when you have your non-moire, here what I'm drawing is sort of the contours of the the half and quarter metal states in the non-moire sample, and just overlaying commensurate filling of the moire. And what you see is that at, let's say, if you're in a quarter metal and you go to nu equals -1, that just corresponds to occupying a full moire band of this quarter metal, and you get an energy gap. Same thing for nu equals -2 of a half metal, you get an energy gap. And that pattern is basically just repeated everywhere that you look. So basically the correlations and the symmetry breaking are already there without a moire, and when you turn on a moire, that gives you the ability to make gaps, and you'll just gap out systems where the degeneracy was right, so that at the given filling you're at, you have effectively now a single particle energy gap. And of course, this can generate enough Berry curvature even just from the moire, as well as from gapping out the original Dirac points, and you can see these churn insulators in various places. And I'll sort of skip that. I'll just mention as the very last thing that these are very clean systems now, right? We can look, and we're starting to see a variety of states at fractional filling. So for this whole cascade here, this is in a topologically trivial band. You can see a whole cascade of gaps at not only at integer fillings of the superlattice, but also at fractional fillings. So a quarter, a third, a half, 2/3. So far, all of these states, at least at zero field, have 0 churn number, but they can develop churn numbers at quite small fields. So it seems like maybe you can do things like have a Wigner crystal that's pinned to the superlattice, and then see either some kind of competing symmetry broken churn insulator. Maybe you can think about it as a Hofstadter butterfly inside that Wigner crystal potential in these types of states. And so we're just starting to really explore this. And obviously, what would be a dream would be to see something at fractional filling in a churn band that maybe has a fractionally quantized Hall effect. We have not seen that yet, or I promise I would tell you about it. So anyway, let me end here. I think I'm anyway running over time. So so thanks everybody, and thanks for your attention, and thanks to the organizers for inviting me.
Yeah, thank you, Professor Yang, for a wonderful talk. And we got a question coming in. So let me read it. The first question is, the orbital magnetism comes from the self-rotating of block wave function and from center of mass circular motion. May I know which one is larger in your observation?
Yeah, so I mean, of course, it depends on the density that you're at, but as terms of an overall effect, the center of mass is, when you have a churn insulator, the center of mass motion seems to be the bigger effect, because you see Let me see if I can go back to that slide. You see a big growth of the magnetization in sort of absolute terms when you're in the energy gap, and that's all coming from center of mass motion. So that's this. So basically, the fact that you see, this is a measurement of this signal, our magnetic field signal. It gets big in the energy gap. That's all coming from center of mass motion because this term is zero. You're not occupying any bulk state. It's all coming from the Berry curvature and the edge states. So that is the bigger effect as far as we can tell. But then, of course, it all later gets canceled by a countervailing contribution from MN. So I mean, it's a little bit of an ill-defined question. It depends on the density. Does the orbital ferromagnetic state break any lattice symmetries? Is an interplay with elastic degrees of freedom possible? Or sorry, should I read the other one first, maybe?
It's fine.
Okay, yeah. They're tied for upvotes. So is an interplay with elastic degree of freedom possible, especially in the domain formation? So orbital ferromagnetic states break any lattice symmetries. We have found such states. I didn't tell you about them. You can certainly find ones that will double the unit cell. That's sort of an interesting topic of its own. We don't think the interplay with elastic degrees of freedom is very likely because the strength of the kind of structural pinning is very big and the energy differences between these interacting states are extremely small. So I actually think that, magnetostriction or things like that seems to me kind of unlikely, just because the energy scales are so far off. But the electron system certainly can, break lattice symmetries. And we've seen, I mean, the last thing I showed you is certainly an example of that. And there may be more spectacular examples where it actually will spontaneously break lattice symmetries in a Chern insulator, and which we have a paper on arXiv you're welcome to look at. So yeah, that can certainly happen. May I just continue reading the questions from the top, or?
Yeah, sure.
Yeah, okay. So is the superconductivity you observe in the ABC trilayer graphene present with or without the BN-Moiré potential? No comment. Do you have direct evidence that HBN is 0 degree aligned to graphene instead of 30 degree aligned? No, we don't have any direct evidence of the particular alignment, except that we see a very large gap at charge neutrality, which indicates that the HBN is breaking the C2T symmetry of the graphene. Do I think it's possible to observe gap states in bilayer graphene aligned with HBN? No, we tried. In fact, this was something that we tried a long time ago, and now we understand why. So, right, the key thing is that you need the Moiré potential, let's say nu equals 1, to overlap, to be at a density where you have a quarter metal in the non-Moiré system. Okay? And in ABC trilayer graphene, that works out because all of this stuff happens at pretty high density. So that means that this quarter metal, which is this sort of blue region here, can get to the density where you get nu equals 1 for the superlattice. That's fixed by the lattice. This can only be, this is as low as you can make that density for graphene HBN because HBN and graphene have a lattice mismatch. So there's just a maximum Moiré wavelength that you can get. In Bernal bilayer, where was it? All of this happens at considerably lower density. So I think, well, okay, let me take it back. It is possible. It's just we need to go to some very, very large, I think I need to look at the numbers, but nu equals -1 is going to be something like, 0.75 or 0.5, 10 to the 12. And you can see the quarter, this is the quarter metal. It doesn't quite get there. And the half metal gets there, but now you need that to get the nu equals 2. So you're talking about some gigantic displacement field. And I don't think that's going to work to get you there, at least with that way of making a Moiré. So anyway, so that, yeah, the short answer is I don't think that will work just because the densities are too low. And the detail is that there are additional hoppings in the ABC band structure, which are kind of key to making all of this stuff happen at finite density. They just don't happen in Bernal bilayers. So it's a detail, but that's important for making all this happen at finite density. Okay, what's the resolution of the nanosquid used? The resolution is about 200 nanometers for most of the measurements that I showed you. How is the orbital ferromagnetism depend on B parallel? Is there a transition to spin polarized state? We have not studied this carefully, just not for any particularly good reason. I think David Goldhaber Gordon has studied this in more detail, and there is a transition at sufficiently large fields to a spin polarized state, as far as I understand. Let's see, why is there a gap at n equals 0 and d equals 0 in ABC trilayer? Aren't the valence and conduction bands connected? Is the gap in many body effect? If so, what is the state? No, it is a single particle effect. Okay, at 0 displacement field, sorry, let me find the right. At 0 displacement field, the valence and conduction bands are connected in the single particle picture. Actually, we do see some kind of gap state there. That's a many body effect. You can't even see that on the plots that I'm showing you of the data because that's happening at very small displacement fields. As soon as you apply an electric field, these bands gap out because you can think about that degeneracy is really protected by inversion symmetry, and that the inversion symmetry is relating, an atom on the top layer to an atom on the bottom layer, and once you lift that, then you lift that band degeneracy and you just get a large single particle gap. So yeah, that's a trivial gap. It's exactly the same as the electric field induced band gap in Bernal bilayer graphene, and that's the insulating state at 0 density and high displacement fields at, yeah, sorry, maybe the question was actually about 0 displacement field. There is a small gap, but it's but that's some many body effect that we don't understand. Can you comment on the observation of superconductivity? I cannot comment on them from the Berkeley group. I think I'll have more to say about that in about a week. What's the broadening of the twist angle inhomogeneity? Is it possible to realize superconductor in BLG or TLG? The broadening of the twist angle inhomogeneity, I'm not sure exactly what units you want there, but it's similar to what was observed in other, by STM groups and by Ellie's group. It's kind of comparable. I can look at the numbers, but 0.01 degrees over some tens of microns here. This is I think in degrees per micron or something like that. Are there controlled studies of the effect of twisted angle disorders on TBLG, comparing transport property of systems with different degree of twist angle and homogeneity? I mean, I would say that yes, if you remove the word controlled, every study of twisted bilayer graphene is an uncontrolled study of the effect of twist angle disorder, and I think we're just now starting to try and really piece together, the microscopic connections between, in a given device, how much of, what does this mesoscale disorder really mean? I think that, my guess is probably, there's some, there's advances, let's say in these twisted trilayers seem to be more uniform. These ABC structures are more uniform. My guess is that the controlled experiment will be just eventually to figure out how to remove this and then see what survives and what doesn't and what's important. It is very time consuming to actually correlate, structure and function on the transport level in this way. But I think that, the community overall is sort of always trying to find cleaner systems, and I think with increasing success. So.
Yeah, thank you, Professor Yang, for giving the talk, and it's wonderful, and we are all looking forward for your coming result. So
thanks.
Yeah,
Stay tuned.
thank you.
Yeah. All right. Bye.